Okay. Hi everyone. So my name is Kel Zin, and today I'm here to talk about Diophantine equation, which is a very interesting topic in cryptography. So recently I've done some of the CTF challenge, and I encounter this kind of question quite often. So I just think that it would be nice for me to give a short talk on how to and on this topic. Yeah. So the first thing, I'll introduce some of the basic concept of the Diophantine equation, and then some applications, and last I will just focus on some examples question that I have solved. Yeah. So the basics. So Diophantine equation is an equation where only the integer solution matters, and we actually have met this kind of equation a lot in our life. Like for example, we have the Pythagorean triple. So this Pythagorean triple is the this one is A, this one is B, and this one is C. So is the side of a right angle triangle. And as you all know, like most of the time we only care about the integer solution. We don't care about the other things. So A should be an integer, B should also be an integer, and so on. And another very interesting one is the linear equation. So this linear equation is given A, given B, given C, and then you want to find x and y such that ax plus by is equal to c. And yeah, so this can also be related to the Bernoulli's lemma. I don't think I spelled it correctly, but yeah. So basically, if C is a GCD of is a multiple. So if C is a multiple of GCD of A and B, then the solution exists. Yeah, so this one is the one for linear equation. It's okay if you are not familiar with it, it's fine. Yeah. And then the last one is the Fermat's Slug Theorem, which is a very intensively researched topic. So this one says that when n is larger than 3, I think it's larger than equal to 3, and we don't have a positive integer solution that satisfies the equation. Yeah, and that's some of the examples for the equation. And then it's actually not easy to solve one. So there's this guy, this mathematician called David Hubert, and he has like 23 problems related to mathematics. So in his 10 problem, this is a problem that seeks for a proof for a general algorithm that solves every Diophantine equation. But then it is proven that such an algorithm cannot exist by Yuri Matyasevich. Yeah. So just an idea that it's not easy to solve a Diophantine equation. And Diophantine equation actually occurs a lot in cryptography, like for example the ISA. So this one is if you are not familiar with ISA, it's fine. But just for those who know ISA, so we have this message M, and then we raise it to power E, we get C. And then we can actually rearrange the equation to something like this. And the power of E minus C is equal to 0. And then we let this to be a function, something like that. Yeah, and then what we care is actually the integer solution for this equation. Yeah. And it's also the same for Diffie Hellman. So Diffie Hellman is just change the E to A and to G, and then you've got the elliptic curve. So in elliptic curve, this equation occurs a lot in elliptic curve because this is the equation for you to check if the point is valid or not. But it's not important. It's just for you to, if you know this, then it's good to know. Okay. Yeah. And now I'll just move on to some examples problem that I've solved before. Okay, so yeah, before I go to here, any questions so far? Yeah, for the front. Yeah, you can type in the chat if you have any questions. If not, then also just move on. Yeah. So okay, yeah. So I'll just move on to the first example. Okay, this is a challenge on Crypto CTF 2021, and it's called T2. And it's the description basically says that cryptography is coupled with all kinds of equations very much. Yeah, and the code is just like this. It's very short. You can even fit it into a slide. Like that's not possible for most of the challenges in CTF, but in crypto, most often things like that will happen. So yeah, you can see like you can kind of read this code. So basically, the flag is what you want to get, and then this L is the length of flag, and then the flag is split into two parts, which is M1 and M2. So this part, the flag is split into two parts by half. Okay, and then basically you convert the string into integers and the string into integers, and then the question gives you a text string, and then the next thing is this assertion. Basically says that x to the power of 2 plus 1, this kind of this whole thing. So this thing holds. And then just by knowing this, they want you to find the flag. So in the case that, so x is actually representing M1 and y is representing M2. So they want you to find this flag. How can we do that? Okay, so like I mentioned just now, the flag is split into two parts, x and y. And then the only hint we get is just this. So this is the assertion. So, and we need to find out the flag from this equation. And if we rewrite in mathematical notation beautifully, so what we get is this. But then the question is, how do we solve this? We want to find x and y, but we only have this equation. So how? And the thing that we know is that x and y are integers, and they are very similar in big length. So it means that the size of the is very similar. Yeah. So you can do it the root way. Basically, you simplify the equation. So you take this and then you move the 4xy to this part, and then you expand it out, and then you find out that it's actually x plus 1 squared multiplied by y minus 1 squared, and it's actually equals to 4k. And then you can take square root on both sides, and then you get this. Yeah. So you can do it this way. So this is one of the way of solving some Diophantine equation. Basically, you try to expand it out and then factorize, and then see whether you can get something out of here. And then because once you know this, it's actually very easy to get x and y. Because we can find all the possible x and we can factorize 2 to the square root of k. And then this one will just give us all the possible factors. And then from all the possible factors, we just combine some of them, and then we can get x plus 1 or y minus 1. By knowing x plus 1 and y minus 1, basically can get x and y. Yeah. So it's very hard. Like it's not intuitive for you to actually do this. Like you need to, like from here, how do you know that from here can go to here? This is not easy, definitely. And so how can we solve this kind of question? Of course, if we have if we are very intelligent, and then we have a great brain, possibly we can solve this by hand. But then so the thing that I want to introduce is we can solve this with SageMath. So SageMath is a tool. It's a very powerful tool. So it's very similar to MATLAB or some Mathematica and so on. So basically, you can use SageMath to do a lot of mathematical operation. And then what you need to do is just put in the equation and then dot factor, and then you get the result. Yes. And then you solve the question. So the solution is actually less than 3 lines. Not less than 3 lines. It's I mean, if you include some of the like x and y, what are the values and some logic stuff, so it can be solved in around maybe 10 lines. Yeah. So I think this is one of the nice thing about crypto, is that you can solve a very a question in a very elegant way. And SageMath is a great tool for you to do on this, because you can just use this dot factor function, and then you get factors. Yeah, just like that. And then if you want to factorize a number, you also use dot factor. Yeah. And this is the first example. Yeah. Any questions for this whole part? You can just type in the chat if you have
How do you get from these 3 lines to the flag?
Okay, so by knowing the factors, right? So by knowing the factors, you get this, and then you know that x plus 1 times y minus 1 is equal to this. So this must be a combination of the factors of 2 times the square root of k. This must also be a combination of 2 times square root of k. So you can get a factor like, so if you know that this is actually equals to f1 times f2 times f3 and so on, fn, you just combine some of them, and then you check whether it looks like the flag. Yeah. So yeah, so yes, that's how it works. And then by knowing x and y, you get a flag. Okay. Yeah. So
yeah, I have a question. Sorry. So can you like run us through what is your thought process when it comes to like this kind of questions when you first see it? Like, do you immediately know that like, oh, it's this kind of equation? I can't pronounce that name, that's why I say this kind. But is it like, how do you figure it out?
okay, so first thing is you analyze the question, and then from the question you know that the only hint you get is just this part. So you must juggle with this equation, and that's the only thing you can do, because the all the things up here doesn't give you any knowledge of how x and y will look like, and this is the only part that will give you the idea. So what you can do is that you just write it out in the equation, and then you just look at it and try to think what can you do with this equation. And because you don't, of course, you don't know if the factor is in such a nice shape. So what you can do is you just one of the method is you just plug it into SageMath, and then you just write dot factor, and then you see whether it's nice or not. If it's not nice, then you need to use another method. But in this case, the factor is very nice, so it's good.
Okay, Ken, thanks.
Yeah, generally it's very ad hoc to solve this kind of question, but this is one of the methods. Yeah. Okay. Then I guess I'll just move on to the next one. So this is also from Crypto CTF, and then it's just another solving equation problem. So you have these 3 equations that is given to you, and then from these 3 equations, so you they have x and z and y, and then they use this x and z and y to generate the prime for RSA. So this is the prime for RSA P and Q, and so if you know x, z, and y, you basically solve the whole thing because you get P and Q. Yeah, and then the question is back to how can you solve this whole chunk of thing? Okay, and it's very easy. You just solve it, right? So A1, A2, and A3 is given, and then if you can somehow juggle this one into x, into some form that you can get the equation. So you know, like when we are in high school or something, we kind of deal with this kind of like x plus y is equals to 1 or x minus y is equals to 2 and so on, and then we try to solve for x and y. So this is actually the same thing, but then it has some powers and some multiplications. The degree is higher. So how can we do this? Okay, let's analyze some of the methods that we can use to do. So first we can move the A1 back here, and then we get this 3 equation. And then if it's possible to combine the equations and rewrite in terms of one variable. So let's say just like for example, like I just use back the same example, like x plus 1 is equal to 1 and x minus 1 is equal to 2. So we can just take these 2 equations and add it together, right? So if we add it together, we manage to eliminate y, and then we get 2x is equal to 3. Yeah. So the idea is very similar. You just want to find a possible, if it's possible to combine the equation and rewrite in terms of one variable, like x to some power, x to some power, and so on, then we can solve this using some numerical methods, like for example, Newton's method. So it's easier to solve it, to solve an equation when you have only one variable. And then this Newton method is the way that you calculator solve this kind of equation. if you remember. Yeah. And yeah, so how can we do this? Also by using SageMath. Of course, you can do it by hand and then try to do some multiplication and so on, but it's hard. It's really hard. Just by using SageMath, we can write. So first we declare two variables x, y, and z, and then P1 is the equation, P2 is the equation, and P3 is the equation. And then we use this magic function. This is a magic function. So you take P1 dot resultant P2x. What it does is it's basically combining P1, combine P1 and P2, such that after the combination of this one, the equation you get will not have x. So this is what it means. You combine P1 and P2, and then you get an equation that is only contains z and y. But then you might have a larger degree. Yeah. So you get what I did was just P1 dot resultant P2 x. So here you remove x. So x is removed here from here. X is removed. And then you plug in this equation, and then you resultant P3 again. So here y is removed. And then you use the sage find root function dot roots. And then you get the value for z. So this is the value for z. Yeah, it's just that. So this looks very complicated, but it actually can also solve in less than 10 lines. Yeah. Yeah. And then you get your flag. Yeah. Any questions for this part? Okay, how exactly does the resultant work? This is a very good question. So Sage actually just extract everything out for us. But if you're interested in the internal implementation, so let's say if I have a equation like x to some power plus x to c1, and then c2 x to some another power and so on. And then we also have maybe k1 x to some power. Okay, so I think I should write it more clearly. Okay, so yeah, so if I have c1 x a1 plus c2 x a2 and so on until cn x an 0, and then we have k1 x b1 and so on, k2 x b2 until k n x n. If you want to combine these two things together, you can check out a method called I think it is called the Salvester Matrix. So by using this method, you can combine these two together into one resultant. But then, what if you have multiple unknown values, like multiple variables? So if you need to consider if you need to do the resultant of multiple variables, you need to there's a algorithm which is called the Macaulay's. I think it's spelled like that, yeah. But Macaulay's method or something, yeah. So this is how the resultant works internally. If you are interested in it, you can check more about it. Yeah, but I will not go through it how it works internally. I just show the tools that are given to us. Yeah. Any more questions? Okay. Then we can just, I guess, okay. Then we just go on to the next one. Okay. So this is the last question, which is so this is interesting. So this is from ASCS 2021, and the question is basically like this. So there is a point on the curve, and this is an elliptic curve. So what the author did was like, so x is the flag, and then y is the xy is a point in the curve. So this is a point in ECC curve. So the ECC parameter is given here, and then you assert x at y and assert yx. So it means that this point when you swap x and y, it's still a valid point inside the curve. And if you write it into an equation format, it's basically this. So to really understand why you get this equation, you need to have a basic knowledge on how ECC works first. But then if you know how ECC works, it just means this. So you get y squared equals to x cubed plus ax plus b, where a and b is known, and then you get x squared equals to y cubed plus ay plus b. And then it can solve with the exactly same method. You just get the resultant of f, and then you remove the y, and then this is just some syntax in Sage. Basically, you want to convert this into a univariate polynomial before you can find the roots. So this f dot resultant y will give you a polynomial that only contains f. So that only contains x. And then by having this polynomial, you can just look through all the possible roots, and then one of them will be the flag. Yeah. So that is what it is. So the solution is also less than 10 lines. Yeah. And yeah, so that's the end of my presentation. Okay, so I basically just give some of the examples, and then hope that you can learn some of the techniques to solve certain Diophantine equation, and then appreciate the abstraction given by SageMath, so you can do a lot of polynomial multiplication, addition in SageMath, and love crypto more. Yeah, so that's all. Okay. Yeah. Any questions?
I have a question. How do you know all the names of these functions? Because every time I open the SageMath website, there's so many functions and none of the functions are usable.
Yeah. That is a good question. So basically, you have to have some knowledge into some of the syntax that is used by Sage. So for example, for this one, you want to create a polynomial. So you want to call it a polynomial with two variables. So this is a polynomial ring. But then the actual reason why is it named like this is you need to have a higher level of algebra knowledge before you can really understand why the syntax is such. But then you can actually just copy from the examples on the documentation. So Z basically means integer. So this means integer. So if you put Z here, it means that x and y can only be integer value. If you put QQ, then means that it can only be rational value. Yeah, value. If you put GFP, so this GFP says that it is a field in mod with P, with only P elements. So basically just mod P. So why am I using this GFP right here is because of the equation. So we have this one, right? So x is equivalent to y cubed plus ay plus b. So you notice the mod P here. Yeah. So if you're dealing with some prime mod, so then you can use GFP. Yeah. But note that this P must be prime. If you want to have arbitrary modulo value, like for example, if you want to just mod n, so and like let's say if I put like for example we take RSA for example, okay, so m to the power of e is equivalent to 3 mod n. So this n is not a prime number, and what you can write is in Sage syntax you basically write it as z mod n. So that's kind of different syntax that you need to know. But then I think the best way for you to know to learn might be learning algebra in a higher level. But then learning a higher level algebra, but then that is not possible for most of us because we don't really have the time to squeeze out time to do that. So if you don't have this kind of interest in this, maybe you can just copy from the documentation and then get the sample codes from there, and then try to juggle it around and see whether it works. So any more questions? Yeah, so maybe I just talk a little bit more about some of the some other interesting one. So like sometimes we don't have, so like in this case, like you can see in this case, we have 3 equations. If we have 3 equations and we have 3 unknown, most of the time we can actually just write it into a equation in terms of 1 variable. But then what if we don't have enough equations, and then we have more unknowns than equation? Like for example, we have x plus y is equals to 3 or something. So this, of course, we have infinite amount of solution right here. But then so there's a technique which is called the lattice. You can use the lattice construction technique. So if you know that this x and y is rather small, then you can use this lattice construction technique to solve this kind of equation also. Yeah, this is extra knowledge. Okay, yeah, I guess if there's no other question, then I can just end my presentation.
Yeah. Okay, so good evening, everyone. My sharing today will be on image forensics. And before I begin, just a quick introduction about myself. I'm Jian Hao. Like many of you here, I'm majoring in information security in NUS, and my hobbies are on gaming and technology, especially for security domain side of things. So I think Nigel has already done a great introduction about my background. So let's get right to the talk. Okay, so for the agenda for the talk today, I'll be sharing about what a digital image is, which is mostly some theory and background on it, followed by motivation of image forensics. And lastly, I will show some applications of it in capture the flag challenges. And just a quick disclaimer, while I am interested in image forensics, I am no subject matter expert in this, but I'll try my best. So to begin, a digital image is basically a representation of bytes to represent an image. So it could come in form of a vector of image, which are images represented by mathematics, or raster image, which are represented by pixels. I am sure some of us here have zoomed into images before and realized that our pictures are formed by those tiny square blocks, which are pixels in an image. So for the talk, I will be focusing on raster images as they are most commonly used. Raster images basically uses a bitmap method of representing pixels on a rectangle grid, like the Pikachu we have here on the slide. They may come in form of like various formats, which I think many of us here would be familiar with, such as JPEG, PNG, and GIF. And with some format, there will be some sort of different schemes which determines how information about the picture is represented in binary data. So these format schemes could determine things like the fidelity of the colors represented, the color ranges, the transparency, as well as how information is arranged for file size optimization. So for formats like JPEG, usually there will be some form of compression being applied to the image, even though they are usually not noticeable to human eye, so that we can save this storage space or network bandwidth as we transmit them over the internet. Then we also have formats like PNG, which supports lossless compression. Okay, so as an example, for Jpeg encoding, right, it has several interesting properties. So firstly, instead of using RGB, which stands for red, green, blue, we usually use as a syntax to identify colors, right? JPEG uses YCDCR, which is a family of color spaces that uses blue-red differences in image along with the luminance and brightness to determine the color space of each image pixel blocks. This is because this color space is more efficient than the traditional RGB color space, which introduces lots of redundancy, which is a waste of storage space and bandwidth, which are often limited. And the second thing is that it uses quantization tables, so to encode pixels in 8x8 block for downsampling, where they apply discrete cosine transformation. This table can usually be found in forensics tools and can be used to scale their quality level. So why is there a need to understand image forensics, you may ask? I believe that besides interest and fun facts, right, one importance of digital image forensics is to enable us to understand how information can be modified and hidden through these media formats, which relates to the field of information security. For example, in recent years, we have the advancement of machine learning and deepfakes are getting more common, where people can just download the software and modify the image at ease while producing rather realistic looking fakes without going through the trouble of Photoshop, which might require some experience from the user end. And when authenticity cannot be verified, right, we will have problems, especially these days where fake news is prevalent and there are many people from trolls to nation states who are interested in fabricating images and information online to push their agenda. And by understanding forensics, we can at least attempt to identify a fake image from the real through various telltale signs, which I will cover later. Another reason to learn is because it gives us the skill to perform and identify steganography, which is the practice of concealing a message within another within the picture or physical object, like in the image on the slide. So one could possibly hide some text with super tiny font in the big image. With information on the image being represented by bits, one could also modify a certain segment of the image to hide their ASCII message, since everything can be represented in bits. And true, of course, this is a very simple example for layman explanation, and more often than not, steganography involves more complex manner of hiding information. So steganography is quite common these days in both CTF and also used by threat actors to hide information to avoid detection. So one common and popular example would be Loki bot, where it hidden code inside the image before using a script to extract information and run the payload. While this, there are also arguments on the relevance of image forensics challenges in CTF. I think they are still helpful for people to learn about the potential of hiding and passing information through discrete means, and no harm scoring some CTF flags at the same time, right? So in this talk, I'll be going through how I would approach a typical CTF image and the rationale for using various tools. But please take note that this is not exhaustive and there are many other techniques and tools out there depending on the author's creativity and sophistication in hiding information. So usually when we download a binary image file, we will want to screen the file first for low-hanging fruits. And we can do so by screening the file through various tools. Then if we cannot find the information by screening, then we will spend more time diving into analyzing the image. So the first thing I would usually do is to run the file command to check if the binary I downloaded is what it claims it is. And sometimes CTF organizers or like the files we download online have fake extensions or no extensions. And we make use of file which this file command to look at the magic number of the file to guess what it is. So to act on, right, magic number is usually a unique sequence of bytes at the start of and the end of the file, which is chosen by the file format creator to allow programs to identify the file they are reading. So common magic numbers are in the slides, which are referenced from Wikipedia. For those interested, you can read up more about magic number, as it's an interesting concept that applies to most file formats, even not images, but binary files like executables. And one cool thing about file is that it also passes some information about the picture, such as the dimension of the image and the color map. So once we have confirm that the file is an image file, I would usually run tools to check the metadata. This can be done in many ways. If your operating system have some built-in image editing tools, you could just right-click on the file and look at the properties for some of the EXIF information. And to do this analysis in a more comprehensive manner, we could use EXIF tool command. Oh, and EXIF stands for exchangeable image file format, and it's usually attached to images file when you take a picture using your digital cameras or your smartphones. They tend to contain useful information for the end user, such as the geolocation, which can be used in open source intelligence challenges to identify where the photo is taken, or other more technical information like the time, the manufacturer of the device used. If anyone used like Apple Maps, Apple Photos or Google Photos, this is how your devices is able to map your pictures to the location. And in this slide, I have a snippet of the command for installing EXIF tool for those who are interested. So let's say this is our target picture. We want to figure out more information about it. By just taking a quick glance at it, we can only tell information that this picture is taken at some street in the daytime, and there's a building with some bells. So by using the EXIF command on the image, we can see that the picture is taken on a Nikon Coolpix P6000 camera, and it gives you the details about the software, byte order, date time that is taken sometime during 2008, October 22nd, during 4 p.m. And many of the details related to the photograph, such as the flash status, focal length, and more. And if we just want specific information like the GPS, we can just pipe the output to grab and throw the leg and long into map softwares online to get information about where the photograph was taken at. But be careful about this, as EXIF can be edited by anyone using tools, and they do not guarantee the accuracy or authenticity of the information shown. And with that, we would have the approximate location of the image. And in this case, it's somewhere in Italy. Next up, one common trick in CTF is to check if there are any hidden files within a file. This could be used for many binaries besides images too. We can make use of automated extraction tools like binwalk to save us time. For those who are interested, we could try this tool called binwalk by running the command binwalk-e with the file name, and it will extract out the files for you by looking at magic signature patterns like the magic numbers. And yeah, that's how you get the flag in some CTF, as seen in the screenshot in the slide. And besides binwalk, another common approach would be to use strings. It's a rather useful utility in many CTF categories, as it allows us to get human readable strings from binaries, which might give us some hint or clue about how to solve it. And in this case, right, I just had to pipe the output to grab with the flag format. And since this is a challenge from Pico CTF, we just use the keyword Pico here and we would find the flag. And unfortunately, if at this point, after all the screening and with the tools you have, looking at the strings and the metadata, and you still do not find the flag, this is where we have to look for steganography. For steganography, usually we would use scripts or software to hunt for information, as doing manually is very inefficient given how there are thousands of bytes in an image. And in the interest of time, I will not be going through all the tools again for steganography, but I'll be listing some of the more interesting ones here on the slide. And if you are interested, you can find out more perhaps in the future for CTF challenges. So the first tool I'll be using is StackVeritas, which is quite new. It supports quite a lot of file formats and even has support for Docker, which is quite cool. So I thought it can save us some time and effort for those people who want to set up. Okay, so for the image that I'll be working on is on the right, cute dog picture that I used previously for the binwalk example. So StackVeritas is quite simple to use. You just run the command along with the input file, and it will do all the processing for you. and it outputs lots of useful information, which I covered earlier, which without needing you to run the commands yourself, from the information like EXIF extraction to the file extraction. So another cool feature about the tool is that it does automated image manipulation. So what it does is that it's basically manipulating the colors, the contrast, and the luminance of binary file of the image file into many of these variations, as sometimes flags or information may be concealed this way. And yeah, it also does the same extraction like being walked earlier to extract the hidden files using signatures, which could help us in finding the flag, like in this case. And another cool steganography tool I usually use is this online GUI tool at 29a.ch called Forensically. It's a free tool and requires no sign up, and best of all is that everything is on your browser. So it has a wide range of tools like magnifier in the screenshot if you want to zoom into pictures to find information. Not sure if everyone can see the image, but the magnifier is on histogram equalization mode now. And in layman terms, right, this allows us to see the contrast better, which is useful when you want to have an image which is either like very bright or very dark. So you can tell the information between the foreground and the background more clearly. And if anyone has done Photoshop before or used other image editing tools, I think clone stamp will be very familiar to you, where it copies an array of pixel information and pastes it to another place in the image. This is not so CTF related, but more on the forensics, as it shows artifacts that a picture may have clone stamped by checking the pixel similarity level across the image. As you can see, the tool actually highlighted regions which were clone stamped in purple and showed where the similar group of pixels are. And when in contrast, if you look at this image, you can tell that there are suspiciously similar looking clouds in the sky. Yeah. And it also features error analysis tools, basically due to compression in image, right? When someone tries to edit an image and paste or create information on top of an original image, their error level and luminance tend to be different. So there would be some differences in each pixels. And thankfully, without diving into all the technical details, forensically analyzes the image for you to point out like what may have been added or edited. So in this case, right, the UFO, which obviously is fake, has a higher level than the rest of the image. And this contrast can be made more obvious by tweaking the values of error scale. Another cool feature would be the noise analysis. In digital image, right, noise is usually a random variation of brightness or color caused by the image sensor when taking photos. So for example, for older cameras, you realize some weird white lines or like those small dots when you try to take pictures in dark environments, like in the slide here, some of the examples. So in forensically, this tool does a reverse denoise to remove the image and only show the existing noise on the image. How this helps is to let you see the difference in the noise level across the image. As the UFO is taken from another image source, the noise level is different and therefore highlighted on this tool. Likewise, on the top right corner, the image of the paraglider is also of a different noise level. And last but not least, there are many other cool features like thumbnail analysis, which is able to get the original image recovered in poor quality, which might give you some clue about what should originally be in the image, as opposed to this edited picture where the paraglider and the UFO is edited with the addition of the shadows and the clouds in the background. And the last tool that I want to share today is another alternative website called Stack Online. This tool is open source and available on GitHub for those who are interested in exploring the source code. I think what is cool about these recent years is that we are having more and more tools for steganography, and they tend to be more user-friendly as compared to the past. And for this tool, we just have to follow through the graphical user interface and upload the file we want to analyze. So on the website, you can also play with the colors to see if there are any artifacts. And here are some of the many images output from playing with the bit planes. They are quite fun and colorful, besides finding the flag. And yeah, just by clicking a few buttons on the website to manipulate things like RGB, inverting the colors and bit planes, I have managed to find a flag quite easily. Likewise, Stack Online also supports data extraction and allows the user to manually choose how they want to extract data. And in the case where through some trial and error, I also managed to find a flag. While not optimal as there are tools which brute forces data extraction, I suppose it's not a bad tool for those who want to look into the image in a more manual manner with more control over the parameters. And in the interest of time, I'll be stopping here. If you are interested, there are many other tools out there like StackBreak, which does brute force or word list attacks on the image to recover information. There are also other steganography solvers which looks into artifacts like the most and least significant bit color channels to try to recover information for you, which I think Nigel will discuss more in the next talk later. And another rather new and interesting tool would be Basecraft, which does auto carving of EXIF to detect possible encoded text like base64 and tries to decode them for you. And it also does OCR on the image to save you some time of like finding an OCR or manually typing out the flag from the image, which can be quite troublesome when some of the CTF authors like to make the strings very complex with symbols. And normally most forensics and CTF challenges involving images can be solved with these tools. And if all else fails, I suppose we just got to boot up like Photoshop or image editor and try to manipulate the image ourselves or dig deeper into the binary data. And in this case, perhaps tools like Python imaging library Pillow might help. So the possibilities of hiding information within an image is endless, and sometimes it just got to involve creativity and understanding of the underlying image format. So yeah, thank you everyone for your kind attention. I hope my talk gave you some interesting insights into digital images and made you a little curious about pictures you see every day on the internet. And if there are any questions, I'll be happy to take them. Oh no, there isn't a flag in the Nyan cat image. That was just for fun to show some ASCII art. And yeah, if there are no further questions or if you have any further questions after, you can always email me. And I guess if no further questions, I will hand the time back to Nigel. Thank you.
Okay, so let's begin. The title of this talk is called Hoodwink, and we'll be talking about steganography in some detail, but it's not a deep dive by any means. For today, we'll be covering a few things, starting with what is steganography, and then we'll be talking about some primaries or things that you will need to know in order to understand LSB steganography, which is the main topic for this for my part. And once we know what LSB steganography is, we can take a look at some applications in real life, in particular digital watermarking. So chapter 1, what is steganography? To answer this question, I think it might be good, it might be most instructive to ask another question, sort of like a small exercise. So what we have here, right, is a PowerPoint. And let's say I send this over to Kel Zin, and then Jian Hao is like the FBI agent spying on our chat. He intercepted this PowerPoint, and he knows that inside slide 4, there is a hidden message. So now for you guys, right, the audience, I'll give you 15 seconds. Try and guess what the hidden message is, or minimally, how did I hide a message in this slide? So you guys can think about it for a bit, and later I'll review the answer. Okay, so the time is up. And so as it turns out, right, I'm pretty sure none of you would have guessed it, but the message is hidden here. Sort of like in invisible ink, you know, if you get what I'm trying to say. If I am right, most of you would start to look at the words and think like, oh, is there like a certain pattern? the punctuations, how is it used, why do they use like olden English and things like that. But and this really brings us back to what is steganography, and it is the art of misdirection. In essence, we're trying to hide things in plain sight, where people do not think to look. And I think this part is especially important, so much so that I had to underline it, where people do not think to look. And it takes a lot of experience and creativity to be able to understand how humans think when met with a certain new piece of information. As is often the case, the medium is the distraction. So like just now, right, when you see this, right, it's text. And so the brain instantly starts to look at the words and start to try and interpret the meaning behind those words. And just like that, your brain is already setting you up for failure, because it gives you tunnel vision. When you only look at the medium and you focus on the content, it will oftentimes you'll miss anything. You miss everything that you, in places that you do not think to look, right? It's not possible for you to find what is hidden. So that is essentially what steganography is, the art of misdirection. Okay, so now let's talk about some basic information you'll need to know in order to understand what LSB steganography is, which we'll cover later. And actually, I requested to go after Jian Hao because he would explain to you what an image is. So just a quick recap. Over here on the right, we got a very blown up picture of Charmander, and an image is essentially a collection of pixels, but more formally, an image, you can think of it as an m by n matrix or 2D array, where each entry is an 8-bit unsigned integer. So for convenience, right, we'll just be using grayscale images or black and white images. Of course, for RGB images and things like that, it is still a okay, like you can think of it as a 2D matrix where each entry is a tuple, or you can think of it as a 3D matrix, 2D matrix with a depth of 3 for R, G, and B. But for the purposes of this discussion, we'll be sticking to black and white images. So 2D array, where each entry is an 8-bit unsigned integer from 0 to 255. 0 means black and 255 means white. So if you take a look at the original image, right, the outline of Charmander is very black and the eye is white. So you can see in the corresponding pixel values, right, it's 0 all the way for the outline because it's black, and it's 254, so very close to white for the eyes. So this is what the numbers mean. So we were still talking about like basic information that you need to know. Apart from knowing what an image is, here's a little exercise that will hopefully prepare you for what is to come later. So let's play a game. I'll modify a pixel in this image, and I need you to guess which pixel was modified. So, so this is round 1 of spot the difference. And here are the 2 images. So maybe you guys can take a look at it for 5 seconds and tell me which pixel was changed. Okay, so time's up. Hopefully all of you got it. So at the upper top right corner, you can see that the pixel was changed. And there's a very scientific reason why you are able to spot this difference so quickly and easily, I hope. And it's because the pixel value changed by a lot. So in the original image, right, the pixel value is 237. And in this modified image, the pixel value is 0. So there's a lot of contrast there. And that is why you were able to spot it. So pretty easy, right? Now let's take a look at spot the difference level 2. All right, so this one is considerably harder, I would think. So maybe you guys can take like 15 seconds to try and see which pixel has changed. If anyone has any idea, you can just type in the chat. I will see if anyone got it. Okay, so time is up. Seems like okay, never mind. Not too sure was Jian Hao. Okay, so we've got some answer, and hopefully you guys have some idea in your own heads as well. And as it turns out, right, no matter what, hang on. Okay, so as it turns out, right, no matter what pixel you choose, you would have been correct, because I changed every single pixel in this image. More precisely, I flipped the LSB of every pixel in this image. So you can see the outline of the Charmander's body used to be all 0, right? So I flip it, now it's all 1, as you can see the outline. And the eye, right, it used to be 254. and now it's 255. Because 254 is just all ones except the last one, which is 0. So I flip the LSB, it becomes 255. So it's extremely, I think, astounding, you know, that at such a low resolution, when you can see every single pixel of the image, of the base image, you still cannot tell that when every single one of the pixel has been modified. And so that is at the heart of what LSB is about. Because what it tells us is that changes to an image's pixels at the LSB level are imperceptible to the naked eye. So with this understanding, we can move on already to what exactly is LSB steganography. And sorry, for those that might not know, right, LSB just means least significant bit. So whatever number you have in binary form, right, just take the rightmost bit. Okay. Again, to answer the question of what is LSB steganography, right, it might be helpful to ask another question of theoretical interest. Given an image with dimensions m by n, can we hide a file of size mn bits? So hopefully, if you're following along so far, right, the answer is yes. But how? So let's say you have a file that is has mn bits, and you've got the bit string here, all lined up nicely. And we know that the target image that we're going to hide the file in, right, also just nice is an m by n matrix. So what you will want to do, right, is take this bit string and make a line break every n bits. And this will give you a matrix of dimensions m by n. And this is, of course, it's a bit contrived for the purposes of this example that both are exactly of the same dimensions. But let's say, right, the image is m by n, so that has that number of pixels, and your file has m by n bits. What you can do is superimpose this bit matrix onto the target image, and you get something like that. You can see a very nice one-to-one relationship already, where each bit in the bit matrix will correspond to 1 pixel in the base image. And so from here, right, we just need to set the corresponding pixels LSB to whatever is in the bit matrix. So the first pixel in the image, right, we'll set it to 0. The LSB of the second pixel of the image, right, we'll set it to 1, and so on and so forth, according to whatever the bits of our file is, so and so. And if you do that, this is the end result. We've got the original image, and then we modify the LSBs of every single pixel one by one according to whatever our file is in binary, and then we'll get the modified image. And just so you know that I'm not like smoking you, right? You just take a look at the first 4 pixels of the modified image. The LSB is 0, 1, 1, 0. So actually you can do this very quickly. An even number will always have an LSB of 0, and an odd number will always have an LSB of 1 because computer science. So if we take a look at the original bit string, right, it does start with 0, 1, 1, 0. So that is correct. We want to embed our file into this base image, and this is the resulting modified image. And most importantly, they look exactly the same. Imperceptible change to the naked eye. So yeah, so that's the whole idea of steganography. We do things in plain sight. Our only defense is the person that's looking, right, will never guess that this is how we're doing things. And of course, Jian Hao brought up many very sophisticated ways of identifying whether an image has been steganographically modified. Okay, actually, maybe I'll talk more about this later. So let's just continue with the talk. So we've covered what steganography is, the art of misdirection. We talk about some things we need to understand LSB steganography, such as what is an image and how exactly changes at the LSB level are seen by the naked eye, which is imperceptible. And then we talk about how LSB steganography, where any binary file, right, that can be encoded as 0s and 1s can be hidden inside an image. Of course, the file cannot be larger than the image. And then, so that's how LSB steganography works. Now, let's take a look at some practical applications in real life. Of course, you can just use LSB steganography to hide whatever file you want inside an image, send it to your friend, and hope that the FBI can't find out. But apart from hiding, there are more interesting applications of steganography, as we'll show later. So let's consider a problem from the real world. I went to Google movie footage leaks, right? And so these are some of the top results. And interestingly, we got this. Yeah. So you can see this, right? A video leak from Spider-Man No Way Home, and there's proof that it's real. Some footage from Spider-Man was leaked online. So how can we use what we have learned to solve a problem like that, or maybe not solve, but let's say you are a stakeholder in the production of Spider-Man and something like this happens, wouldn't you want to know who leaked it? And I'm telling you that we can, but how? Using what we've learned. So let's recap what we've learned, which is really only one thing, how to hide a sufficiently small computer file in an image. So for those of you who are interested, interested in these kind of things, I give you like 15 seconds to think about it. Okay, so the time is up. The idea is we want to mark each distribution, or you want to add a watermark to every copy of the video that you release internally. So let's say, right, okay, I'll say what's on the screen first. So a video is simply a collection of images or frames. So when I say 60 frames per second, it's basically they show you 60 images in 1 second to trick your brain to thinking that it's moving. And then what you can do is you tag each video distributed with a text file with a description of the recipient and like the event, how you sending the person, why is that the case. And then this text file, you just embed it in the first frame of the video. So imagine that you got this trailer, right, that you are sending to 3 people exactly, Alice, Bob, and John. So for as a precaution, for security reasons, these 3 videos that you send to these 3 people, right, you mark them individually, say like, okay, this one is for Alice, I'm going to hide the text file in it. This one is for Bob, I'm going to hide a text file in it. This one for John, I'm going to hide a text file in it. And that will look something like that. For Alice's version, right, your text file can be simply like, recipient is Alice, head of the post-processing team, responsible for ensuring that issues with lighting and textures are fixed, and sent to Alice on the 22nd of March. And for Bob, same thing, just a text file. Bob, head of publicity, in charge of deciding if a certain trailer is sufficiently engaging for release, 25th March 2021. And last one, for John, head of development team, need to send it to him so that he can pack it up in the cloud. Sent to him on 22nd March 2021. So we watermark each of these copies that we distribute internally. And how does this solve the original problem of video leaks online? Because so this is how it solves the problem. If you did this, right, you watermark everything that is distributed internally. If there is a leak footage, you can just when it is leaked, of course, after that, right, you just download the leaked footage from the web, and then you extract the first frame and you extract the embedded metadata, which is just this text file. Then you will know exactly who was the leak, or so it's Alice, Bob, or John, and this will you use digital watermarking to solve the problem of video leaks. But I think more generally, right, you can say that you can use this for things like intellectual property and intellectual property mainly. So this is the end of my talk, but maybe just some closing remarks since I'm like the third person. Firstly, we had Kel Zin talking about cryptography. Then we had Jian Hao sharing with us how people actually how the police work, how they catch people who try and do this kind of thing. And now I'm teaching you like the very basics of like how the thieves work. So how they try to hide things in other stuff. So it is but this is still very elementary. There are a lot more sophisticated ways to perform LSB steganography. So some closing remarks is Jian Hao share with us how it looks like from the perspective of the police. But what is important to note is that for a lot of the techniques that try and find out if some image has been steganographically modified, right? All of these techniques are probabilistic. They will never be able to tell you for sure whether this has been modified. Maybe let me phrase that more accurately. They will never be able to tell you if an image has been modified with the intention of hiding something inside. So maybe the image, right? Maybe it's just due to noise or like some issue with the transmission. That's why the bits in the actual image maybe a bit lossy or something. Then yeah, it gets flagged as being like steganography modified. But no one can tell you for sure whether the person that sent this image, right, did he hide something inside? So that is a probabilistic solution. A lot of the tools that we have out there, and almost certainly for anyone who knows what he's doing with steganography, right, it will be very difficult to extract the exact binary that was hidden inside the image for many reasons that I will not go into. And for those of you who are interested, right, especially if you took a class on signal processing, if you're familiar with this thing called the discrete Fourier transform, there's a cousin called the discrete cosine transform that takes a 2D array and then gives you another 2D array. So you transform the array into another domain. And how a lot of the more sophisticated LSB steganography people will do it, right, is that they change, they take the original image, they put it through a DCT transform to get a second 2D array, and then they do the LSB operation there before they convert before they do the reverse DCT. And as it turns out, right, if you do it like that, it is extremely difficult to find if a file has been hidden inside, because there's 2 layers of abstraction and work. And the last thing I want to add on is that steganography and cryptography are kind of direct opposites. Cryptography is sort of like we encode something so mysteriously that you one look and you know is something is missing. It looks super suspicious, but you will not be able to find out what is the actual content. Whereas steganography, on the other hand, is you take one look at it and you think, oh, okay, looks normal. So it totally like passes you by, and then you will never know that something is hidden there. But in real world, right, people usually combine both. Just like how RSA uses both symmetric and asymmetric encryption. So asymmetric for the exchange of the symmetric key, and then they start using symmetric encryption. What people usually do in real life is whatever they want to hide inside a file, right, they first encrypt it, and then that encrypted file, they hide it into the image using steganography. So again, 2 layers of defenses. So a bit of knowledge for fun. So yeah, this is the first 3 parts: cryptography, image forensics, and now steganography. Yeah, I think that's the end of my part. Let me see if there's any questions. Okay, if no one has any, if anyone has any questions, can ask. Otherwise, I'll be passing the time over to Brandon.
Okay. So good evening, everyone. Today I'll be presenting on Xsc Attacks. So this form of attacks is based in the domain of web exploitation. So it's a little bit more different from what the previous 3 speakers have been presenting on. So yeah, without further ado, let's get into it. So this is the agenda for my presentation. Firstly, I'm going to talk about the motivation for presenting on Xsc. After that, I'll go into a bit of background info, which is essential for you to understand how exactly Xsc Attacks works. So it's pretty much just a primer on XML itself, as well as like the different terminologies within the XML syntax, such as entities, etc. Thereafter, right, I'll go into the vulnerability itself, which allows XSCs to exist from. So yeah, just analyzing the XML syntax and seeing where exactly are these flaws that can be exploited. And then lastly, I'll just go into a few examples or case studies like showing XSCs and how they can be used. So firstly, I'm going to start with the motivation. So why exactly am I covering XSCs? So firstly, right, XSCs, they are actually part of the OWASP top 10. So if you don't know what OWASP is, it's actually just a list of the top 10, the top 10 highest web-based vulnerabilities. So this list, right, is usually compiled regularly, like every 4 years, if I'm not wrong. So from OWASP 2017, right, so you can see in the picture, XSC is one of the most like popular vulnerabilities. It's under A4. actually in the newest OWASP, which was compiled this year, it was reclassified under security misconfiguration, but it's still one of the top 10 vulnerabilities. If I'm not wrong, security misconfiguration for OWASP 2021 is A5. And also, right, XML is still very prevalent in today's applications. So while it is true that there are more popular formats such as JSON, which are being used for data transportation, right? XML is actually still very popular. It's used in many applications such as Office, Microsoft Office, as well as APIs like SOAP and file formats like SVG. So now I'm just going to go into I'm just going to go more in depth about XML before I explain to you about the Xsc Attacks works. So what exactly is XML? It is a markup language. So what this means, right, is that it's a system for formatting and displaying a document text, which is similar to HTML. The main difference between HTML and XML, right, is that HTML is used for data representation, whereas XML, right, is used for both data transportation as well as sometimes data storage. So, for example, as you can see in this image, right, in this diagram, there are different parts of an XML structure. So, firstly, right, you have your metadata, which is the first line in the XML file. I'm not sure if you can see my cursor, but I'm pointing out this question mark XML version equals 1.0. This line over here. So basically, what this line does is it specifies important information for the XML parser, right, to take note of when it is going through this XML, this markup. So, for example, what is the version of XML used, and there is sometimes other metadata that is included, but this is also optional in some cases. And below this metadata, right, you have your root element. So over here, right, you can see on the right side, the root element here is a product listing. So every XML document, right, it must have exactly one root element. And inside this root element, right, you can have nested attributes. Or for example, over here under product listing, right, you have other attributes such as product. So these are known as children of the parent, where the parent is the root element. And then again, it can become nested even further. So under product, you have even more children, like name, description, cost, etc. Okay. So for XML documents, right, there are a few syntactic rules which you need to adhere to. So firstly, right, the text must be case sensitive and they must match with one another. So that means if you open a tag called name, right, you need to make sure that you close this tag with the same name. So you cannot just open it and then then go off and do something else. The document will become a malformed basically. And also, right, you can see here special characters such as angle brackets, right, and quotes. They are not allowed in XML documents directly. The reason being because they will obviously break the XML structure, and then when the parser tries to pass this, right, it will throw an error. So these special characters, right, the parser is not able to interpret if they are part of the input or they are just a tag. Okay. So how exactly do you work around this, right? You use these things called entities. So what exactly are entities, right? You think of them as simple storage units, like variables. So for example, right, in this code over here, what I do is I assign an entity with this entity called name with the value of John. So if you think of it, right, in the equivalent, the C or Python equivalent, right, is basically saying char star name equals to quote John close quote. So it's pretty much like defining your variables in your normal programming languages, right? So what this does, right, is that now you have your entity, which you are able to use multiple times in the document if you want to reference it elsewhere, right? And the thing about entities, right, is that they are defined in this region of the XML document called the doc type. So what this doc type means, right, is that this region is referring to this region as your document type definition. So instead of writing the value John, right, directly under here, right, what we do is we define the storage unit, our entity, within our doc type DTD, and then we refer to it within this name text over here. So it's like basically just invoking our variable, right? This is especially useful when you want to reuse the same group of code like multiple times. So for example, if you want to reuse a certain function or a certain calculation, right, you can just refer to it using this entity. You don't need to retype the same few lines of code within the text that you want. So for those of you who are familiar with HTML, right, there's a similar concept. This is a similar concept to the extends syntax from a base HTML file. Okay, so there are different types of entities. So earlier, right, what we saw was called the general entities. So what happens is that you define the entity first. You define your entity first within your DTD, and then you reference it later within the actual XML data. Okay, but there are different other types of entities. So later we'll be covering also predefined entities. So what these are, right, are special character entities, right? They can, they are these parameter entities, right? They are only valid within your document type definitions. And what this does, right, is that when you define, it allows you to define an entity, right, within another entity. So you can see here, it's like you are able to define nested entities. And this will be especially useful for Xscs. So we will come back to this later. And the next one is predefined entities. So what this means is that these are special character entities that can correspond to the predefined values. So if you recall earlier, right, the example on these angle brackets, right, instead of using the open angle bracket text directly, right, what we can do is we use the hex representation of the angle bracket in SC, and then we put it into our within our XML text. So this basically corresponds to your open angle bracket. Okay, so now that you are primarily on XML and like entities and DTDs, right? So now we can start going into what exactly are Xsc attacks and how they are carried out. So entities, right, they are not just used for storing values, but they are also capable of a lot more. So XML, right, offers a lot more features, such as, right, they not only can store the value that are specified by you, such as like this string, but they can also pull data, right, from a local file, or they can also make a request, right, to external resources or domains, and store these, right, all these as entities for future use. So you can see here, right, these two sources, right, are already like a cause for concern already. So you can kind of see like that's where the flaw is originating already. Okay, so how exactly can we use external entities? So here, right, we invoke the system keyword. So system, right, it basically tells the XML parser, right, that the entity over here is an external entity. So this instructs the parser, right, to fetch the resource, the external resource, right, and then store the data from the resource inside your entity itself. Okay. So if the external resource is similar to the XML syntax, right, it will actually cause an error. So there are different types of XXEs. There are in-band XXEs. So the example on the previous slide, right? So this is an example of in-band XXEs. You are from your XML data, right? You feed it to the parser, and then from there, right, you are able to directly see the output involved. Okay. There are two other types: error-based XXEs So error base is similar to a blind Xsc. You don't actually see the output. So what you do is you feed the XML to the parser, right? And then it will return you like the error information. So in a way, it's more similar. It's similar to your blind SQL injection, where you're working based on like on the response codes or the information that's returned from the server side. The next one is out of band XSCs. So this one is actually a pure blind XSC. That means what you do is you feed the XML, you feed XML data to the parser doesn't return you anything. Okay, so you need to do some form of out of band request, right, in order to exfiltrate the data itself. Okay, so so before I go more in there, right, a bit more on document type definitions. Document type definitions, right, they aren't part of XML data. So like I said earlier, right, there are a different region from your XML data. They lie above the root element. So from the root element downwards, right, that is the start of your XML data. So the DTD, you can think of it as like in between the metadata and the actual XML data. Okay, so they are defined in a separate header above this XML data, right? And they can be loaded externally, just like normal entities. Okay, so basically how we can take advantage of this, right, is that we can specify a URL, right, at the time of process, and at the time of the processing, right, the XML parser, it will fetch the external DTD which we have specified in our doc type, and it will pass its contents. So this is a double-edged sword for most application developers, right. This allows them to organize their XML data more cleanly by defining their entities, right, in organized files, right. But this also means that attackers, right, are able to take advantage of this and like store entities in these DTDs, right, in order to invoke them when taking advantage of them and exploiting these XXCs. Okay, so what this means, right, is that now I can use external DTDs from within the XML markup itself. Okay, so oops, sorry. So yeah, for this example, right, I'm just gonna talk a bit more about I'm just gonna show a few examples on document type definitions. So for this example, right, we have an internal DTD, right? Internal DTD refers to basically this doc type here. And what I've done, right, is that I have defined a parameter entity, right, which can be referenced by other entities. And this parameter entity, right, is only allowed to be referenced within the DTD, which means that I cannot call parameter entity, right, in my XML data. Okay. And then, right, in the XML data, the markup, right, you see within this pwn text, we have the general entities. So these general entities are what can be called. Okay. So for the XML code, right, a bit more explanation of overall what this is doing. So the parser, right, it will first look at the first line, our metadata. So it will look at the metadata. It says, oh, okay, this is XML version 1.0, right? It will process the markup based on this version of XML, right? Then what it does after that is it looks for the document type definition defined within the same XML document. So it looks for this doc type text, right? And then it passes everything. It passes the entities within. Okay. So for this percent symbol, right? This percent symbol over here, the parser, right, it will pass this as a parameter entity, and then what it does, right, is that it assigns this value, the markup of the general entity, as the value of the parameter entity itself, right? Okay. Then after that, right, we reference parameter entity in the subsequent line. So we are basically calling the value of parameter entity. So what this does, right, is that the value over here, the general entity, right, it will be defined within the DTD itself. Is it in my next slide? Yeah, over here. So you can see, right, the general entity is defined within the DTD itself. So yeah, so this yellow portion, right, it will replace this purple portion over here. So the end result, right, is now that we are able to access the general entity value in our XML data via the phone text. And we know that we can access the parameter entity, right, directly inside the DTD. So you can, from here, right, you may think, right, okay, so this is good. We can just call whatever we want inside our parameter entity. And then in our XML data, we just invoke this parameter entity, and then that's it. We are able to carry out a successful Xsc attack. Okay, so okay, so first, just a small question, right, on blind Xsc attacks. What exactly is this program trying to do? Okay, so firstly, right, this parser, what it is doing, right, is that it will read and store the contents of etc/password in our passwd entity. Right? It's a parameter entity because we want to use this inside the document data type definition, right? And then we define a separate parameter entity called wrapper. So wrapper, right, it will pass the value of the general entity called send, right? And when this PWN text, right, they reference the wrapper entity, it will make a request to an external resource with the contents of the file /etc/password. So basically what it's saying, right, is that this send, right, it will be defined within the document type definition, and then we then call it within the XML data itself. So yeah, so this is the end result of what it should look like. It allows us to read the contents of /etc/password and then send it to the external resource using the Xsc. So in theory, right, this should work, right? But when we actually try to call an actual parser to go through our data, right, we get an error. So this error is a illegal parameter entity reference, right? So what exactly is a problem? Why doesn't this work in practice? So yeah, so within the specifications, right, for Xsc, it tells us, right, that in internal DTDs, right, you are not allowed to make any parameter entity references. So what this means, right, is you are not allowed, right, to reference parameter entities within a markup declaration. That means if you define an entity password, right, within this internal DTD, you cannot access it you are not allowed to access it at a lower level. What a lower level meaning within entity on the same level, but you are able to reference entities, right, at the same level. So you can see for password here, right, you are not allowed to reference it here because it is basically a lower level entity that is defined by wrapper. But for wrapper itself, right, you are able to reference it here because it's basically at the same level. So there's no problem with that. According to the specification. So yeah, so basically this is the problem. This is why our earlier code, right, doesn't work. We are not able to carry out the Xsc attack that way. But is there a way to bypass this? Actually, yes, there is. Okay, so the same specification, right, the same line from earlier, right, it also says, right, that this doesn't apply to references, right, in external parameter entities or external subsets. So you can see how exactly we can take advantage of this, how we can circumvent this. So we can basically just define our parameter entities, right, within the external DTDs, and then we just fetch our references from the external DTD itself. So what this means, right, is that I can just request, right, make a request to an external DTD file, and then the external DTD file will contain all my malicious entity references. Okay. So for example, in this code here, right, within main XML, you can see that there there aren't any entities that are defined within this doc type, because all of them, right, like I said earlier, they are located within this evil.ddd file, which has all the entities that you need to carry out your Xsc exploit, right? And then you notice, right, over here when in our XML data, when we call send, right, send is not within the doc type, but it's within the evil.ddd file. Okay. And also, right, what this means is that because evil.ddd, right, it contains the same entities from the examples before. The send, right, yeah, so I'm referring to this one over here, this example here. The send, right, it will make a request to an external resource. It doesn't matter whether we have a valid response or not. Basically, right, using this, right, we don't care about response. When the parser passes this data, right, it will be able to exfiltrate the data successfully. Okay. So suppose, right, we have a server running, like a simple HTTP server running, and then, right, we have a netcat that is listening to this server at port 80. So when I send the main XML payload, right, from earlier, the netcat, right, will capture the response. So you can see over here is the contents of /etc/password. Okay. So up to now, right, we just read etc password, which is pretty lame, but what if I want to read /etc/fstep, which has information on mounting partitions? So what I do is I set up a server to query external requests. Okay. Then looking into fstep, right, the first line contains comments. So these comment characters, right, they are not actually XML, but the parser will try to pass this, and then you try to pass these characters as valid XML, so it will break the XML parser. So how exactly, right, do we exfiltrate this data? What we can do is we use the C data keyword, this syntax, which stands for character data. So whatever, right, is within the character data, the opening and closing tags, right, it will not be passed as markup by the XML parser. So the idea, right, is that the start and the end entities, right, they will be referenced as general entities within the data XML text. Ideally, the output should be something like this over here. So you can see, like, data within the data text, right, you have your opening characters, the contents of fstep, and the closing characters. But this doesn't work in reality. Why is that? Because, right, the open angle bracket in the start entity, right, is not well formed. If you recall what I was saying earlier at the start of the presentation, right, if you open something, right, you have to close it within the same entity. So because this is not well formed, right, I define my opening in one entity, and then I go off and do a lot of things, and then I want to define my entity, the closing part, right, in a different entity. So this will not be well formed. The solution to this, right, is to use a combination of parameter entities and your external DTDs. So what we do, right, is we just move all the entity references to an external DTD instead, and then based on the specification, right, this will be valid. So this allows us, right, to read fstep. So we read fstep, right, we define the two entities for start and the end text, start and end here. We also use the wrapper entity, which has a general entity, right, with all the other parameter entities inside, and then we just call it within the DTD. So this will allow us to actually read the contents of fstep when we use it in the data text. Okay. Yeah. So this is a lab example on out of band Xsc. But I think in the interest of time, I don't think I have time to go through this. So basically, the goal of this lab, right, is you're just using parameter entities to make the XML parser, right, issue a DNS lookup and HTTP request to web collaborator. So if you're more interested, right, you can go to portseeker.net and just search Xsc with out of band interaction using parameter entities. And this will they'll show you how exactly to use the doc type definitions to invoke out of band Xsc. So yeah, so lastly, right, these are just a few CTF examples which I have come across previously. So yeah, and all these CTF challenges, right, they are using Xsc. So if you're interested, right, you can go look into some of these. They'll basically teach you more about the applications of Xsc. So for example, the Google CTF, right, they use error-based Xsc injection, which is what I was covering earlier. So you can if you're interested, you can look more into this challenge. It's called BNB. There's another one, right, which shows you how Xsc can be combined with other exploits like local file inclusion over here in Sunshine CTF. And then lastly, right, there's a bug bounty online, right, which I found out. It talks about using a blind out of band Xsc with in the PDF using a PDF document to issue like DNS and HTTP requests. So if you're interested, you can look more into this and yeah. So that's all for my presentation. Sorry for overshooting. If you have any questions in the chat, yeah, I can just take those. Okay, if there's no questions, then yeah, that's all from me. Thank you.